This video is created for the Linux Operating System and Development Environment course at Melodon University. And in this module we're going to talk about hard and symbolic links in Linux. So most of you should probably be familiar with shortcuts in Windows. So you have them on your desktop and you see them as some logo type on the desktop and some description beneath it. And if you double press on the shortcut, it will take you to some other path in your system, like in the C drive and the games folder. So you have the shortcuts on your desktop so that you can more easily access your applications. In Linux, we have a similar feature called links. And the whole idea with a link is that we have one file which is not in itself a file, it actually points to another file. So in this case, inside the home folder we have a file named log, but if you try to access it, you will actually access the file /var/log/syslog. So you could say that this file points to the other file. And you can have a lot of separate files that points to the same file. So I try to demonstrate 4 separate files on the system that points to a specific file on the hard drive. So there's not really a upper limit on how many shortcuts you can have or how many links you can have on your system. But there are actually different types of links in Linux. We first have the symbolic links. We will then talk about hard links. So one could say that the symbolic links are the easier types of links in the system. And they actually point to a destination target using absolute or relative paths. So with your file, you have another attribute which is actually the target. So to your link you point to a specific target. And you specify the target with an absolute or a relative path. So in this case, if the link is /home/christian/link and the target is /var/log/syslog, this will actually point to the absolute path of the syslog file. In the second case, however, this points to a relative path. So the relative path depends on where the link is stored to begin with. And we will go a little bit deeper on that. Because if you type a relative path when you create the link will remember the relative path. So it will not convert that to an absolute path. And that is something that is pretty important to remember. So this is a valid link. And this points to the parent directory of the parent directory. And you can actually create symbolic links with the ln command. And you specify the symbolic flag. You specify the target of your link. And the target is actually the file or folder that you want to point to. At the link argument, you specify where do you want your final link to be stored. So in order to create the links that I specified as examples, we could run the following commands. We run the ln command with a symbolic flag. We specify the target. This was the absolute path to the syslog file. And where do we want our link to be created? Here we specify the relative path to the logs file, and we specify where do we want our link to be stored. We can verify our symbolic links by specifying the L flag. So this will show us that this is actually a symbolic link that points to this specific path. And make special note that it actually lists the relative path here. So it will list exactly what you type. Can that cause some issues, you may ask? Well, let's take this specific example. So this is a file structure. We first have the root folder. We have a home folder underneath the root folder, and a link named logs in our home folder. We have a binary text file named syslog.txt inside our var folder. So let's see where this link actually points to. Well, firstly, it points to the parent directory of the home directory, so that would be the root. Then it points to the var directory, and then finally it points to the syslog directory. So this is a fully valid link that points to the syslog file over here. So if we try to read this file or edit this file, we will actually edit this file. It will just send us to this file if we try to open it with some tool. But let's say that we move this link into the netcenter folder instead. What will happen? Well, let's try to follow the path again after we move the link. So first it points to the parent directory of the netcenter directory. Then it points to the var directory, but there's no var directory inside home, which will mean that this link is actually broken. We will not be able to use this symbolic link to access any files because it has a broken relative path. So with this, I would suggest that if you work with relative path, you should relative links, you should actually specify absolute path most of the time. So if you don't have a specific reason to specify a relative path, you should specify an absolute path. Otherwise, you might find yourself with issues like this if you try to move the links in the future. So that's a good thing to keep in mind. So now I want to go into the hard links. But first I want to make you known to a concept that everything is a file in Linux. And all files are stored as index nodes, and those are also known as inodes. So all files on your Linux system and all directories on your Linux system are somehow associated with the index node into your hard drive and into your file system. So there's a large table of index nodes of your system, starting from 1, and it just increments with each index node. So if you create a file, you will have a new index node for that specific file. So 2 is reserved for the root directory. So you always know that index node 2 is the root directory of your system. And your home directory might be 1337 for example, or 2000 or something. So it dynamically associates these numbers to newly created directories and files. So in this example, we associate, so this is wrong. The root should be number 2. I'm sorry about that. But the home/home/Chris in this case is 1338. So this index node stores information regarding this directory. And this is a file, and it has index node 1339. So this index node contains data about this specific file. So how are the metadata about these files stored? So how does these inodes look like, the data structure of those? So in this table, the data structure would actually be this column right here. So first we have an ID. So that is the inode ID. But then we have a data structure that explains the actual file that's stored in this inode number. So how does that data structure look like? Well, we have information regarding who is the owner of the file, who has access to the file, what is the size of the file, when was the file last modified, and we have information regarding what data is included into this file. So we have some tables for pointers that points to data on the hard drive in some way or another. So with these pointers we can point to the data and we can access the data of the file. So please note that the data is actually not stored within the inode table. So we only have pointers in the table. So the table is, the data structures are fixed size in Linux, and we only point to the data from these inode items. So this is how a file would look like. So we store the data somewhere else, and we point to that data from the inode table. A directory works like an ordinary file, so everything is a file in Linux, as I mentioned earlier. But the directory have a fixed way of listing files. So you could say that a directory is actually another table that stores the files that are included into that directory and the inode numbers of those files. So that would actually be the file name of the file that's included into the directory and the actual inode number of that file. So that means you can actually change the name of a file in a directory without having to change the inode number. So these inode numbers are used to point on where to find data for files that are included into directories. So if our user says that I want to read the contents of my file.txt, the system will actually look inside this directory. It will look at, okay, first it will try to find my file.txt from the directory table. It finds it right over here, and it will check what is the inode of that file. And then it will look up that file from the inode table and print out and read the data from that inode. But you can actually store files in separate directories that points to the same inode, as you see in this example. So the text.txt that's inside /home/Chris, that points to the same inode as my file.txt that's inside the Lisa directory. So what does that mean? Well, if Chris tries to edit the text.txt that's included in his home directory, it will actually also modify the version that Lisa has in her directory. because it's actually the same file on the hard drive. That will also cause some issues if both Chris and Lisa tries to modify the file at the same time. It could cause some issues because it's not it's like trying to modify the same file on the system with two separate users. So it's not optimal. So what happens if Chris deletes this file? Well, there's actually a counter in the system that checks how many hard links are available for this specific file. So in this case, that would be 2. So we have 2 hard links to this inode. The file is not deleted from the system until there are no links, 0 links to that specific inode. So for this file to disappear from the file system, we both need to remove it from the Chris home directory and from Lisa's home directory. And we will see when we verify hard links that we can actually look up how many hard links are for a specific file. So how do we create a hard link? We use the same command as with soft links, but without the symbolic flag. So I say symbolic link sometimes, I say soft link sometimes, but I mean the same thing. So you create hard links by first running the ln command, and you specify the target. And the target is the file for which we want to copy the inode number and use that inode number for the new file that we create. So we do that in this example. We specify /var/log.txt, and we create that link in this location. So that would actually create our file, but it would point to the same inode number, which means that if this file is modified, this file is also modified because they point to the same data. So how can we verify hard links? Well, we can do that with a long listing, and we specify the I flag for inode. So this will actually list the inode numbers for the files and directories in our system. So in this example, I created 2 separate hard links that points to the same file. And the first is stored in the ABBA directory, and the second is stored in the cafe directory. But you can see that they have the same inode number, thus they are pointing to the same file on the file system. So I can actually modify any of those files, and it will modify both. So as I said, this is the inode number. There's also another field in this example where we can actually investigate information regarding our hard links. And that is the 2 that you see right there. So that is actually the link count. So I spoke about that a little earlier, but that is how many hard links are there for this specific inode number. So this file is not deleted until that integer is 0. So let's just try to set up some hard and soft links. So first I will remove all my directories in my home directory to have it nice and clean. Then I will create a folder in my home directory named ABBA, and I will create cafe. I start by creating a file with the contents hello world inside ABBA. I create that with a redirection. So we name that file.txt. Let's first verify the contents of that file. So we can cat ABBA and file.txt, and we can see that it contains hello world. So let's start by creating a symbolic link. So that was the symbolic flag, but we can actually write just an S to make it shorter. So first we specify the target, to which file do we want to point. And here we can just type abba and file.txt. And what should be the name of our link? mylink.txt. So if we do a long listing, we can actually see that, okay, so here are our newly created link and it points to abba/file.txt. If we cat that, we can actually read the contents of abba/file.txt. So let's see if we can move that link to the cafe folder without it breaking our link. So now you can see that something broke. We cannot use our link anymore. And that is because we still point to the abba/file.txt. But from where do we point? We actually point from the cafe folder this time. And there's actually no abba folder inside the cafe folder, thus we have a broken link. So we could solve this by, instead of specifying the relative path when we create the link, we can actually specify the absolute path. So that would actually be /home/netcenter/abba/file.txt. So if we move that to the cafe folder, we can still access the file because we specify it as an absolute path instead, as you can see right here. Great. So let's try to work with the, let's try to create a hard link of that file. So first, let us see how many hard links there are for this file at the moment. So there's only one hard link for this file, and that is this instance of that file. This is the inode number. So how do we create a hard link? We use the ln command. We specify the target, so that should be abba and file. And we can call this hard link.txt. Let's do a long listing and display the inode number information. So this inode number is the same as this inode number, which means that they are pointing to the same area in the hard drive. And now we see that there's two links pointing to this inode number. Let's see if our file in the abba folder also says that there's two links. So this is changed now and it says two links. If we try to read the content of hardlink.txt, we can see that that works. If we move hardlink.txt to the cafe folder, it still works. If we modify cafe hardlink.txt, whoops, this is modified. We can see that both the file that we modified is changed, but also the original file is changed. So that was everything for this video. I hope you learned something, and I'll see you in the next video.